Check one. Check one. Check one. Right. Good evening, everybody. Today we'll be discussing two practicals. Practical number 5 in your practical booklet, which is verification of the law of parallelogram of forces and finding an unknown mass. And then practical number 6, using principle of moments to find an unknown mass. Using principle of moments to find the unknown mass. Okay. Right. All of you are right. Practical number 5. All of you are right. Practical number 5. Verification of principle of parallelogram of forces and finding an unknown mass. And finding an unknown mass. And finding an unknown mass. Right. Look at this carefully. Now, what do you mean by the principle of parallelogram of forces? What do you mean by principle of parallelogram of forces? Very simple. If you represent two forces on adjacent sides of a parallelogram. Now, where do you remember this? You remember this when we learned vectors r squared equal p squared q squared 2pq cos theta. So if two forces are represented on adjacent sides of a parallelogram, the main diagonal will give you the resultant, or the diagonal will give you the resultant. So if you complete the parallelogram here, so if I complete the parallelogram here, there you go, parallel equal to this, parallel equal to that. The main diagonal will give you the resultant. Main diagonal will give you the resultant. The main diagonal will give you the resultant. Right now, if this was P, this was Q, then this will be P, this will be Q. Start from one vector, where it ends, start the other vector, join the initial terminal, resultant. And that's the rule. So what do you mean by principle of parallelogram of forces? If two forces are represented on adjacent sides of a parallelogram, the main diagonal will give you the result. Okay. Under this right theory. Under this right theory. Like this. If two forces are represented, like this, huh? If two forces are represented on adjacent sides of a parallelogram, if two forces are represented on adjacent sides of a parallelogram, the main diagonal will give us the resultant. The main diagonal will give us the resultant. The main diagonal will give us the resultant. Okay. Quickly draw this. Quickly draw this. So two vectors P and Q, things that you know are two vectors P and Q. You are completing the parallelogram. The main diagonal will give you the resultant. Main diagonal will give you the resultant. Okay. Right. Okay, no? So here you go. This is your theory. If two forces are represented on adjacent sides of a parallelogram, the main diagonal will give you the resultant. Main diagonal will give you the resultant. Right. Now look at this. How do you do the practical? So first I'll show the video in a while. Let's learn this first. What we do is, now we have a drawing board. We have a drawing board. Normally in your school lab, this drawing board is there. What we do is, we fix two pulleys. We fix two pulleys such that the centers are in line with each other. We fix two pulleys such that the centers are in line with each other. And then what we do is, we send a string over the pulleys. We send a string over the pulleys. And we connect it to two known weights. Let's say there's a scale pan and a weight. Let's take for a basic example, this is about 50 grams. Total weight 50 grams. Here also scale pan and weight. Here also scale pan and weight. Let's say these also 50 grams. Let's say these also 50 grams. Right? So here you go. On the drawing board, you call this the drawing board. You call this the drawing board. Two pulleys are kept in line with each other such that the centers are in line. String is sent over the pulleys and two weights, known weights are connected. Two known weights are connected. Okay. Two known weights are connected. Now, if I look from the side, what will I see? If I look from this side, what will I see? Now, drawing board is there. Remember, the pulley is slightly out of it, offset, slightly out of it. Then you have the string going over the pulley. You have the string going over the pulley. And then you have the weight connected here. Now, please remember, the string or the pulley or the pan never touches the drawing board. There is always a gap. There is always a gap. This gap is important. This gap is important. So here, string, scale pan, weight, pulley, nothing is touching the drawing board. Nothing is touching the drawing board. So this is technically your picture number 1. This is technically your picture number 1. Then what do we do? Then what do we do? Now we have a drawing board, same as earlier. We have connected a pulley such that the centers are in line with each other. Such that the centers are in line with each other. Now what we do is, we hang a known weight somewhere here in between. We hang a known weight somewhere in between. Now, when you hang a known weight somewhere in between, what happens? The moment you hang it, this will come down. A V shape is formed. A V shape is formed. Now, so when you hang the weight here, a V shape will be formed. A V shape will be formed. Here you go. A V shape will be formed. So here you have the weight, scale pan, known weight 50 grams. I'm just randomly taking now. Known weight 50 grams. And now what you do is, you connect this another weight here. Let's say that is also a known weight. That is also a known weight. First, we are going to verify the principle. Then only we are going to do. First, we are going to verify the principle. So this weight is also known. Now, this is your setup. That's it. Now, before you continue the experiment, you must check if there is friction in the pulleys. So what you do is, you gently pull the center weight down and you release it. Don't pull it a lot. Gently pull the center weight down and you release it. Once you gently pull the center weight down and release it, if it goes back again to the original position, you always look at this joint. If it goes back again to the original position, that means there is no friction in the pulleys. But if you gently pull it down and release it, and if it does not go back again to the original position, that means there is friction in the pulleys. Normally, majority of the time, there will be friction in the pulleys. Always there will be friction in the pulleys. So what you do now is, we'll recap back again. Place the pulleys so that the centers are in line. Send a string over the pulleys and fix two known weights. Then what do you do? Take another known weight. Somewhere in between the two pulleys, you hang it. When you hang it, a V shape is formed like this. Remember, these are also a known weight. Then what do you do? To check if there is friction in the pulleys, you pull the center weight down and release it. If it goes back again to the original position, that means wherever you start, you pull it here. If it goes back again there, that means no friction. If you pull it and release, it doesn't go there. That means what? There is friction. Okay now? Right. Then what do you do? Now remember, in the beginning itself, here on the drawing board, using drawing pins, you connect the A4 sheet. The same A4 sheet will be here. Put in drawing pins, you connect it. Right. Then what do you do? Now there are two methods. I'll teach you both methods. First, you use a plane mirror. What you do is, you take the plane mirror and you slide it over under. Now, I hope you remember, here, there is a gap. There. So what you do is, you slide the plane mirror underneath the string. And when the string and its image are in line with each other, that means not like this, image is here, string is here, not this case. Okay? Image is here, string is also over it, coinciding, that case. So when the string and the image coincide with each other, you take a pencil, and what you do is, you project these points here. There. You project these points here. So at the end, you project those 2 points. Those 2 points will be there on the string. So remember this very carefully. What you're doing is, you're projecting these 2 points on the string. Now, what do you mean by projecting? When the string and the image coincide with each other, the string point is indicated here on the piece of paper. String point is indicated on the piece of paper. Same way we send another, keep a mirror here. String and the image coincide with each other. We place 2 points or we project 2 points on the string. Now, if you take the piece of paper, your piece of paper will be like this. Here there will be 2 projections. Here there will be 2 projections. Now important, where all the string segments meet, that point also we project. Where all the strings meet, that point also we project. So there you go. That is all. So what you do is slide a plane mirror under the string. When the string and the image coincide, project 2 points on the piece of paper. Slide the mirror under the string. Slide the mirror under the string. When the string and the image coincide with each other, project 2 points on the string. Also, where all the string segments meet, that point is also projected there. Okay, no? Clear? Right. So before we continue, let's write this and finish. Let's write this and finish. Let's write. Apparatus needed. Apparatus needed. Apparatus needed. Let's write. Apparatus needed. Right? Huh? Parallelogram of force apparatus. Parallelogram of force apparatus. A small stone or a glass stopper. A small stone or a glass stopper. A small stone or a glass stopper. Of unknown mass. Of unknown mass. Comma. Known set of loads. Known set of loads. Known set of loads. Next one. Set square or plane mirror. Set square or plane mirror. Oh, okay. Set square or plane mirror. Half meter ruler. Half meter ruler. Half meter ruler. Some drawing pins. Some drawing pins. Some drawing pins. An A4 sheet of white paper. An A4 sheet of white paper. An A4 sheet of white paper. Okay. A4 sheet of white paper. And triple beam balance. And triple beam balance. And triple beam balance. Right. Let's write procedure. We connect the apparatus as shown in figure number 1. We connect the apparatus as shown in figure number 1. We connect the apparatus as shown in figure number 1, where the pulleys are connected to the drawing board. Where the pulleys are connected to the drawing board. Where the pulleys are connected to the drawing board, such that the centers are in line with each other. Such that the centers are in line with each other. Such that the centers are in line with each other. Such that the centers are in line with each other. We send a string over the pulley and place 2 known weights. We send a string over the pulley and place 2 known weights. and place two known weights. We send a string over the pulley and place two known weights. Okay. Next point. Next point. Somewhere between the two pulleys. Next point. Somewhere between the two pulleys. Somewhere between the two pulleys. We connect another weight. We connect another weight. We connect another weight. We connect another weight. So that the system comes to equilibrium as shown in figure number 2. So that the system comes to equilibrium as shown in figure number 2. So that the system comes to equilibrium as shown in figure number 2. Write it. So that the system comes to equilibrium as shown in figure number 2. As shown in figure number 2. Next point. Next point. We slightly pull the center weight down and we release it. We slightly pull the center weight down and we release it. We slightly pull the center weight down and we release it. If the center weight moves back to the original state position, if the center weight moves to the original position, if the center weight moves to the original position, we say that there is no friction in the pulleys. We say that there is no friction in the pulleys. We say that there is no friction in the pulleys. But if the center weight does not move to the original position, but if the center weight does not move to the original position, but if the center weight does not move to the original position, there is friction in the pulleys. There is friction in the pulleys. There is friction in the pulleys. Right. Next point. We take a plane mirror. We take a plane mirror and we slide it under the string segment. We take a plane mirror and we slide it under the string segment. And we slide it under the string segment until the string and its image coincide with each other. Not like this, huh? Until the string and its image coincide with each other. Until the string and its image coincide with each other. And we project 2 points on the string into the A4 sheet. And we project 2 points of the string to the A4 sheet. And we project 2 points of the string to the A4 sheet. We project 2 points of the string to the A4 sheet. Next point. We repeat the same procedure for the next string segment. We repeat the same procedure for the next string segment. We repeat the same procedure for the next string segment. We repeat the same procedure for the next string segment. So 2 points here, 2 projections there. Next point. Where all the string segments meet, where all the string segments meet, where all the string segments meet, that point is also projected to the white sheet. that point is also projected to the white sheet. That point is also projected to the white sheet. Okay. That point is also projected to the white sheet. Okay. And we remove the sheet of paper. And we remove the sheet of paper. And we remove the sheet of paper. Okay. Right. Before we continue, let's draw these two and finish. Draw figure number 1, the front view and the side view. After you draw this, quickly draw it. Maybe 2 minutes, quickly draw. And then the next picture is there. You can draw that as well. Quickly draw it. Right. Draw the next one. Right? Okay. Now what? So you have the points there. So few more things to tell. So I used the plane mirror now and showed. I used the plane mirror only and showed. What if you're going to use a set square? Now in your compass box, how many set squares do you have? You have 2 set squares. One is the 30, 90, 60 set square. The other is 45, 90, 45 set square. So any set square you can use. This is the set square. So what do you do? So this is what you do if you are using a set square. Have a look. So this is what you do. You place the set square perpendicular to the string. That means you are keeping it like this. This way straight, you can keep it like this. You keep it like this so that the string won't move. String should not move. So keep it here. Keep it perpendicular to the string. Project a point. Move the set square here. Mark another point. Same way, place the set square perpendicular to the string. Place a set square perpendicular to the string. Move the set square. Once it reaches here, place it back again. Place it back again. Therefore, you get the same points there. Okay, no? Put a sign, right? If we use a set square, we must place the set square perpendicular to the string segment. We must place the set square perpendicular to the string segment. We must place the set square perpendicular to the string segment, such that the string does not move. Such that the string does not move. Such that the string does not move. And we project 2 points while moving the set square. And we project 2 points while moving the set square on the string segment. On the string segment. On the string segment. Quickly on the side, this part. Don't draw the whole thing. Just the set square, the 2 strings, this part inside the sheet of paper, this part you draw it. Quickly draw. So then that toss is covered. No? Quickly draw. Okay, no? So there you go, set square method also, using the set square, we can get the same dots, right? We can get the same dots, right? Now look at this carefully, the last bit. Now you have the white sheet of paper, no? You have the white sheet of paper. You have the points here. Right. Now look at this very carefully. Yeah? I'll go back to the original picture. This one. Now, why is this in equilibrium? Why is this in equilibrium? Because upward forces balances the weight. That means T1 is actually 50 grams. If we assume the string is light, here also T1 50 grams. Here also T1 50 grams. Here also T1 will be how much? 50 grams. How is this in equilibrium? Here also T2 is 50 grams. Here also T2 50 grams. Here also T2 50 grams. Here also T2 will be how much? 50 grams. That means this line segment indicates 50 grams. Now you can put any weight you want. I'm just making it easy for us when you study this. Here T1 is 50 grams. So this line tension will indicate 50 grams. This line tension will indicate what? 50 grams. So that means when I draw this, I must use a suitable scale. So T1 is representing 50 grams. What I'll do is I will take 1 centimeter as 5 grams. Then 50 grams will be how many centimeters? 10 centimeters. Now we take a ruler. I join the string segments here such that this is 10 centimeter. No? Same way, I join here such that this is 10 centimeter. Now I must complete the parallelogram. Now I must complete the parallelogram. How will I complete the parallelogram? Normally the easier method is compass. Sometimes in school, they might use the ruler and the set square both. They'll keep the ruler parallel to the set square and then draw it. But the easier method is the compass method. So you take a compass, measure 10 centimeter, put an arc. Take a compass, measure 10 centimeter, put an arc. So you measure 10 centimeter, here you put an arc. Then you measure here 10 centimeter, here you put an arc. Where both the arcs meet, there you go, that is your point. So what do? You join that point. You join this point and complete the parallelogram. There you go, parallelogram is complete. Once the parallelogram is complete, this is what you should do. Join the main diagonal. Join the main diagonal. Join the main diagonal. Join the main diagonal. Measure the length and check if it is vertical. Now, in reality, it should be vertical. You know why? Let's go back to this diagram. So these two are tension. This will give you a resultant. The resultant should be equal to this unknown weight, right? The resultant here should be equal to this unknown weight. So the job here is you're finding this resultant. The resultant value and this unknown weight value both are what? Same. Why? It's in equilibrium. No? So the resultant weight here, the resultant of these two and the unknown weight here, both are what? They should be the same. That is why we are drawing the parallelogram here. We are finding the resultant. And if we know the resultant, guaranteed we know the unknown weight. Is it clear? So that's the basic rule. So what we do is we measure this length. We measure this length. And from once we measure this length, 1 centimeter is 50 gram means L centimeter, you can find the unknown mass. You can find the unknown mass. Then what we do is using a triple beam balance, you find this mass, you remove this mass, put it and you find the mass. If the triple beam balance reading and the calculated reading are approximately the same, we say principle is correct. We say the principle is correct, right? No? We want the resultant and the unknown weight to be equal. So once we complete the parallelogram, we measure the length. Once you measure the length, you can find the mass. Then you remove that mass, put on a triple beam balance, measure the mass, measured mass, and calculated mass. If they are almost the same, principle is correct. Now what you can do is, whatever unknown mass you hang, the diagonal will give you that unknown mass. Whatever unknown mass you hang and you repeat the experiment, the diagonal here will give you, if you draw it newly again, it will give you what? The unknown weight. So this is your principle of parallelogram of forces. Okay. Shall we write and finish it? Let's write. Let's write. Each string segment in the picture, each string segment in the picture will represent the weights which are hung. 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 In the above example, each string segment will give us 50 grams. In the above example, each string segment will give us 50 grams. Each string segment will give us 50 grams. Each string segment will give us 50 grams. Keep writing. We use a suitable scale. We use a suitable scale. We use a suitable scale. And using the ruler, we draw straight line segments. We draw straight line segments proportional to the weight that is hung. We draw straight line segments proportional to the weight that is hung. Proportional to the weight that is hung. Proportional to the weight that is hung. Then using the set square and the ruler or compass. Then using the set square and the ruler or compass. Using the set square and the ruler or compass. We complete the parallelogram. We complete the parallelogram. We complete the parallelogram. We draw the diagonal, comma. We draw the diagonal. We complete the parallelogram, comma. We draw the diagonal. And we measure its length. And we measure its length, right? And we measure its length. And we check if the diagonal is vertical. And we check if the diagonal is vertical. And we check if the diagonal is vertical. Next point, right? Using the length of the diagonal, we can calculate the unknown weight. Using the length of the diagonal and the scale, using the length of the diagonal and the scale, we can calculate the unknown weight. We can calculate the unknown weight. We can calculate the unknown weight. Next point. We remove the unknown weight. We remove the unknown weight. We remove the unknown weight. And we measure its weight using a triple beam balance. And we measure its weight using a triple beam balance. And we measure its weight using a triple beam balance. And we measure its weight using a triple beam balance. If the calculated weight and the measured weight are almost the same, if the calculated weight and the measured weight are almost the same, we say that the principle is correct. we say that the principle is correct. We say that the principle is correct. And using this method, we can find the unknown weight. And using this method, we can find the unknown weight. Okay. Right. Now draw this. T1 is 50 grams. Don't forget T2 is also 50 grams. T2 is also 50 grams. This is like an example. 1 centimeter is 5 grams. Quickly find 10 centimeters. 10 centimeter, 10 centimeter. Keep arc, draw arc, complete the parallelogram. Draw the diagonal, measure the length, check its vertical. From the length, you can find the unknown weight. Take this unknown weight, keep on a triple beam balance measure. If calculated and measured are almost the same, principle is correct. Okay. Right, draw this real quickly. Draw this. Right. Okay, no. So practically simple. So once you draw the parallelogram, measure the diagonal. Draw the parallelogram, measure diagonal. Length will give you the unknown weight. Okay. Right. Now, what if the vertical diagonal is not vertical? What if the diagonal is not vertical? What are the reasons? Well, there are many reasons. Number one is the string might not be light. String is heavy means tension will keep changing from point to point. Next one. Sometimes if you drew the side view, the weights might be touching the board as it moves. If the weight is touching the board or the string is touching the board, there is some additional friction. That might be a reason. Also, if there is friction in the pulleys, again, the diagonal won't be vertical. Next, sometimes there are knots in the string, knots, like this, knots in the string. If there are knots in the string, there again, what tension suddenly releases. Tension will change. Yeah. So those are generally the reasons. Sometimes the weight mass we have taken, but we forgot to take the mass of the scale pan. Remember, if the string has weight, that weight also has to be added. If the scale pan has weight, that weight also has to be added. Example, if you put 50 gram weight, scale pan is 5 grams, then 55 grams here. If the scale pan, if this is mass is 50 grams, scale pan is 10 grams, 50 plus 10, 60. So you must draw this for 60. The scale pan weight also should be what? Added. Okay, no? That's right. If the diagonal is not vertical, if the diagonal is not vertical, the main reason for it may be, that's right, Roman 1, there is friction in the pulleys. There is friction in the pulleys. There is friction in the pulleys. Roman 2. String is not light. String is not light. String is not light. Third one. The string or the scale pan, the string or the scale pan might be touching the board. The string and the scale pan might be touching the board, causing additional friction. Causing additional friction. Causing additional friction. Next one. There might be knots in the string, knots, K-N-O-T-S, knots in the string, which may cause additional tension. Which may cause additional tension. Which may cause additional tension. Next one. We might have not added the weight of the scale pans to the weight. We might have not added the weight of the scale pans to the weight. We might have not added the weight of the scale pans to the weight when we drew the parallelogram. When we drew the parallelogram. Okay. Right now. So there you go. That's your practical. So this is the fifth practical. So you verify principle of parallelogram of forces. Remember, it's very simple. The whole idea is this. The resultant of these two tensions will give you the unknown weight. The resultant of these two tensions will give you the unknown weight. Okay, no? Right. I will quickly show it. These, of course, from one of my known friends. Practical was done. You can observe this carefully. There you go. So that's the unknown weight. That's the unknown weight. So you can put a known weight here even. Whatever you need. Drawing pins, white sheet of paper, ruler, set square, unknown weight, stone, glass topper, whatever you want, you can put it there. No problem. Whatever you want, you can put it there. And this is your triple beam balance so that you can measure what you call this unknown weight. Okay. So there you go, the setup. Pulleys are kept in line with each other. Known weight here, known weight is also connected. So under it, you put a A4 sheet. Under you put a A4 sheet. And once you put the A4 sheet, under it you put a A4 sheet. There you go. The string segments meet somewhere there in the middle. So drawing board is put. There you go. Right. So there you go. That's the setup. Now what do you do? Keeping the set square, we can mark, project the points where all the string segments meet. And here you go, the plane mirror is kept. Now look, on the side I have kept string and the image. String and the image, quickly we mark 2 points. String and the image, quickly we mark 2 points. String and the image, quickly we mark 2 points. Pull the center weight down, release it. So we want it to come to that point. No? Pull the center weight down, release it. See whether the joint comes to that point. If it comes to that point, that means what? There is no friction. If it does not come to that point, that means what? There is friction. Sometimes if the friction is more, you have to put some oil there. You can put some oil here and here. So here you go. Pull it slightly and release it. Even that you can pull and release. But normally we pull the center weight down. So you keep the set square. There you go. Perpendicular to the string. Mark a projected point. Mark a projected point. Same way you mark a projected point there. Two string segments. Same way you mark it there, same way you mark it here. So now you remove the pins. Now you remove the pins. Now these are your points. These are your points. We draw the line segments. We draw the line segments. We draw the line segments. The center point is marked. That is 50 grams. That's also 50 grams for our example. So I took a suitable scale, 1 gram, or in other words, 1 centimeter is 5 grams. 1 centimeter is 5 grams. So this length is 10 centimeter. This length somewhere here, 10 centimeter is to be marked. Keep a ruler. Mark 10 centimeters. Keep a ruler, mark 10 centimeters. There you go. Here to here you mark 10 centimeters. Here to here you mark 10 centimeters. Now, this is the method. This is one method of drawing a parallel. You keep one side parallel, keep the ruler here and shift it. Take it there. Draw a parallel line. You can draw a parallel line like this. Or you can use a compass. That's way more accurate. And there you go, the diagonal. From the 0 mark, here this experiment diagonal will come up to almost 10 centimeters. That is also 10 centimeters. So 10 centimeters. So 1 centimeter is 5 grams means 10 centimeter, 50 grams. So the center weight also is 50 grams. If you want, you can measure its weight using a triple beam balance. And approximately, or both are will be the same. If both are same, what happens? Principle is correct. Unknown value can be found as well. Principle is correct. Unknown value can be found as well. Okay. 50 grams. Now we can place an unknown weight like a stone. Now we can place an unknown weight like a stone. And you repeat the same procedure. First you do it for a known weight to prove the principle is correct. Then you connect a unknown weight like a stone and you repeat the experiment. Again, from the main diagonal, you can find the unknown weight. Draw it. .4 centimeter came. So you multiply 5 by 15.4. 77 grams will come, no? 77 grams will come. 77 grams will come. Now you can check this. So unknown weight found. You can take the stone, keep it on a triple beam balance, check. Check and see. On a triple beam balance, you keep it. 77 means move this to 7. 100 gram weights useless, bring it back. That's pointless. 70, okay. 80, it will go down. Bring it back to 7. Now move the 1. Move the 1. Slowly move it. Slowly move it. 77, it will be horizontal. 77 horizontal means calculated weight, measured weight, both are what? Same. Okay, no? Right. There you go. Practical number 5 done. Okay. Practical number 5 done. Now practical number 6. Practical number 6. Right? Using principle of moments. Using principle of moments. Using principle of moments to find the unknown weight. Using principle of moments to find the unknown weight. Right. This is way more easier. What you need is a tall wooden block. Tall wooden block. Then you need a knife edge. You need a knife edge. You need a knife edge. Tall wooden block. You will need a ruler. So this is what you do. First place the ruler on the knife edge and balance it horizontally. First place the ruler on the knife edge and balance it horizontally. Wherever you balance and find the balance point, make sure you mark it with a piece of chalk. For example, if it was balanced at 50 centimeter, put a chalk mark there. Very important. So this is your first step. What is your second step? Second step is, what we do, now this is balanced on a knife edge, no? Now, according to your booklet, This is what they have done. To hang a unknown weight. To hang a unknown weight at a distance x. So this will create a moment in the anti-clockwise direction. Then you hang a known weight. Then you hang a known weight such that it is balanced. Such that it is balanced. So unknown weight I'll take as m naught. Known weight I will take it as m. Now you can find moments about the center of gravity. Very simple, practical. Clockwise moments equals anti-clockwise moments. Clockwise moments m naught g into x. Anti-clockwise moments mg into y. Gg cancel off. If Gg cancels off, this is what you get. M naught x equals my. Y is equal to m naught divided by m into x. You can see now it is of the form y is equal to mx. So what we do is we change this in equal intervals. So if you are taking this in 10 centimeter intervals, if you take in 10 centimeter, here also you vary and find. If you take in 10 centimeter, here also vary you will find. So what you do is, for different values of x, you find different values of y. For different values of x, you find different values for y. And then what you do is you plot the graph. You plot the graph between x and y. Graph is of the form y is equal to mx. Now from the gradient of the graph, you can find the unknown mass. You can find the unknown mass. From the gradient of the graph, you can find the unknown mass. So practically simple. Again, I'll tell you. You balance the ruler horizontally on a knife edge. And wherever it balances, you always mark it. Because every time you hang the weight, you must repeat the same procedure. Then what do you do? You place an unknown weight at a particular distance. Now these are there given in the practical booklet, but you can do it the opposite way also. You can chain this, accordingly chain that also, no problem. Place the unknown weight at a fixed distance and adjust the known weight so it's balanced. Measure x and y. Change x in equal length intervals and accordingly you change y. Plot the graph between y and x, these are in centimeters. Plot the graph between y and x. From the gradient of the graph, we can find the unknown weight. Gradient of the graph, we can find the unknown weight. Okay. Let's write it. Let's write. Apparatus needed. Apparatus needed. Meter ruler, knife edge, wooden block. Meter ruler, knife edge, wooden block. Known weight. Known weight. Unknown mass. Known weight, unknown mass, piece of string. Known weight, unknown mass, piece of string. Let's write procedure. Figure number 1. Let's write procedure. We balance the meter ruler horizontally. Right. Meter ruler as well. Apparatus needed, meter ruler also right. That's right. Balance the meter ruler horizontally on a knife edge. Balance a meter ruler horizontally on a knife edge as shown in the figure. As shown in the figure. As shown in the figure. And place a mark on the center of gravity on the ruler. And place a mark on the center of gravity of the ruler. Place a mark on the center of gravity of the ruler. So if I draw this on the side, knife edge, normal reaction, and weight lie along the same line. Normal reaction and weight lie along the same line. Okay, right. Your center of gravity is there. Next point. As shown in figure number 2, as shown in figure number 2, we hang an unknown weight m0 at a distance x. We hang an unknown weight m0 at a distance x. And to balance it, we place the known weight at a distance y. And to balance it, we hang the known weight at a distance y as shown in the figure. We hang the known weight at a distance y as shown in the figure. Keep writing. If we apply moments about the center of gravity, we can find a relationship. We can find a relationship between x and y. We can find a relationship between x and y. Next point. We change the unknown weight in equal x distances. We change the unknown weight in equal x distances. And we measure the y distance. And we measure the y distance. And we measure the y distance. We tabulate it and we plot a graph. We tabulate it and we plot a graph. We tabulate it and we plot a graph. From the gradient of the graph, we can find the unknown mass. From the gradient of the graph, we can find the unknown mass. From the gradient of the graph, we can find the unknown mass. Now look, when you're doing this experiment, there are small tricks that we use. What are they? We make sure that known mass and unknown mass are almost the same. If known mass and unknown mass are almost the same, what can you say about y and x? Y and x will also be almost the same. So this graph will be a highly symmetrical graph. So we can get a huge range of values as well. Okay? That's right. We always make sure that precautions, right? We always make sure that the known weight and the unknown weight are almost the same. The known weight and the unknown weight are almost the same. The known weight and the unknown weight are almost the same. This will give us a good symmetrical graph. This will give us a good symmetrical graph. This will give us a good symmetrical graph. Next precaution. Every time we balance the ruler, we must place it at the center of gravity. Every time we balance the ruler, we must place it at the center of gravity. Okay. That's it. Quickly draw figure number 1 and figure number 2. Draw below. quickly. So here, X. So if you take the practical booklet, you're changing the unknown weight. And to balance it, you're changing the known weight. From the gradient of the graph, you can find the unknown weight. From the gradient of the graph, you can find the unknown weight. Okay. I want to show you the video also quickly. Quickly, yeah. Take 2 minutes. If you're writing, quickly write and finish. Right now? Okay. So there you go. There you go. Horizontally balanced. Horizontally balanced. So these are the knife edges. Huh? These are the knife edges. You make sure the knife edge is perfect. These about principle of moments. Huh? Principle of moments. There you go, the knife edge. Yeah. This is your 50 gram weight, known weight. That's your unknown weight. There you go. We use a string. So first, before that, you balance it horizontally. There you go. Try to balance it horizontally. So this is your principle. You change the unknown weight. We named it differently. That's okay. Change the unknown weight. And to balance it, we change the known weight. And to balance it, we change the known weight. So this takes time. Huh? It's a time consuming process. So once it's horizontal like that, to take a string segment. Now make sure you mark this point and keep. Huh? Mark that point and keep. There you go. Weight is there. And you balance it here. Never ever place it like this. If you place it like this, we don't know to find exactly where the center of gravity is. Because the shape is different. If I keep a stone here, do I know where the center of gravity is? I don't know. So never place it, always hang it. Now we learn center of gravity. Whenever you hang it with a string, exactly at the bottom of the string only center of gravity is there. So string and center of gravity will be along the same line. So never ever place it like this. Always we have to hang it. Always we have to hang it. Always we have to hang it. Huh? You send a small hook like a thing. So you can send the ruler inside this and hang it. So the knife edge is exactly between 50 and 51. If you carefully look, the knife edge, here you go. Here you go, 50.5. So every time you balance it, you always keep it at what, 50.5. That's the way. Every time you balance it, 50.5 is there. Every time you balance it, you make sure that the knife edge is always at 50.5. Okay. So there you go, you slide the weight. Slide the unknown weight like that. Right, now we know. When the heavy weight is in the corner, the known weight is somewhere here. So heavy weight comes closer, known weight also will come closer. So here it's at exactly what, 27, these at 51 centimeter, 50.5. There you go. Put a small table. I'll move it a bit forward. So there you go. Dot lines indicated goes along the origin. Adjust it to 50.5. So you can measure this. This is your X, this is your Y. So you're going in 10 centimeter intervals means from here 10 centimeter, then you have to bring this closer. Still bring. Yeah, can I bring it a bit more? Now, okay. And finish. X distance can be measured, Y distance can be measured. So where is this kept? That is 50.5. You measure this reading, measure that reading. The difference here only is X. The difference here only is Y. Now you must change this equal distance, then balance that toss. Here, 10, 20, 30, 40, like that. So you're changing the unknown weight in equal intervals. And accordingly, you find what? Y. So I'll move it a bit forward. So now double that location. And this distance y. Now you move that further. This should be in 50.5. Move that further. Again, get it balanced. Again, get it balanced. So we can move one more. Here to move it. Again, get the reading. Get the reading. Later, you can subtract and get the x value. There you go. X, Y now balanced. So taking moments. G and G cancel off. Y is equal to M over M naught. We took the symbol opposite. That's okay. Our unknown weight plus M naught, known weight plus M. So there is no issue. That's a stored. So we have different values of X and different values of Y. Different values of X and different values of Y. So where the stone is, you're moving the stone X. You're moving here 10, 20 centimeters, 16, 22, wherever that's suitable to balance. 28, 34, 10 or 6 or whatever suitable. But these are equal, 6, 6, 6, 6. So you can subtract and see here. Equal intervals. The center of gravity, this part is your center of gravity, 50.5. And this is where your weights were. 50.5 minus 40.4, you get the readings. 50.5 minus 35.4, get the reading. 50.5, like that, you get the balance length. Subtract and get. 50.5 minus this. Now you plot the graph. Now remember, these are practical, exactly done for Royal College students. So this is the exact practical given. So it's like you are inside the Royal College lab doing it. And we have to be thankful for my good friend Kosala sir as well. X-axis or X in centimeters, Y in centimeters. X is the unknown weight, Y is the known weight. So you carefully mark the X and the Y. X is 10, Y is 10.1, 10.1. So you can mark the coordinates. There you go. Then 16, 15.1. Now 15.1 we can't mark because there is a 0.1 there. No? So close to 15 we mark. 15, 15 is there, no? It's okay. You all carefully mark it. Now you can draw the best fit graph. Now you can draw the best fit graph. Best fit graph will uniformly distribute the points above and below the graph. Best fit graph will uniformly distribute the points above and below the graph. Okay. Best fit graph will uniformly distribute the points above and below the graph. So when you draw the best fit graph, check and see number of points above almost equal number of points below. You're uniformly distributing the points. You're not joining all the points, you're uniformly distributing the points. Just show it the way it's drawn as well. Right, best fit graph. Best fit graph will uniformly distribute the points above and below the graph. It's not keeping the rule and sending it through maximum number of points. Huh? The line that you draw should nicely distribute the points above and below it. Okay. So you can see sometimes whatever you found is not in the line. Whatever points you found is not also in the line. But that is the whole idea behind best fit graph. Okay. That's the whole idea behind the best fit graph. And now you select. You select points which exactly cut the grid line. Which exactly cut the grid line. Now this point exactly cuts the grid line. Somewhere here also exactly cuts the grid line. Somewhere here also exactly cuts the grid line. So you take a point where it exactly cuts the grid line, and gradient is what? Y2 minus Y1 divided by X2 minus X1. Okay, now? Y2 minus Y1 divided by X2 minus X1. So look at this carefully. Yeah? Coming back to the point. Now, when we plot the graph, we have points like this. No? Sometimes the best fit graph will distribute the points above and below the graph. Will distribute the points above and below the graph. And then what you should do is, where exactly the grid lines meet. Now you might have a line which goes through the grid line. This is taken. This point is taken. X1, Y1. Same way, exactly cut the grid line. Now this can be taken. X2, Y2. These should be far away. So you can say X1, Y1, X2, Y2. Y2 minus Y1 divided by X2 minus X1. That is your gradient. That is your gradient. Your gradient is equal to M naught over M. Your gradient is equal to M naught over M. From there, you can find M naught. Cross multiply. From there, you can find M naught. Right there. When we draw the best fit graph, right? when we draw the best fit graph, the best fit graph will uniformly distribute. The best fit graph will uniformly distribute. The best fit graph will uniformly distribute and divide the points above and below the graph. And divide the points above and below the graph. And divide the points above and below the graph. We select 2 points which exactly cut the grid mark. We select 2 points which exactly cut the grid mark. Is a grid line which exactly cuts the grid line. We find the coordinates and we find the gradient. We find the coordinates and we find the gradient. We find the coordinates and we find the gradient. Using this gradient, we can find the unknown mass. Using the gradient, we can find the unknown mass. Okay, no? So what do you call this line? Best fit line. Best fit line. Quickly draw below. So now we all know how to do this practical. Huh? You don't keep the rule and draw the line through maximum number of points. You keep the rule and draw the line so it what equally divides the points above and below the line. And exactly where it cuts the grid mark like this. Exactly where it cuts the grid mark like this, those points only are taken. Right? Those points only are taken. Take 2 points. From this, you can find the gradient. Quickly draw it. So remember this, huh? The line here is a best fit line. Now, if I show it here, best fit line. Some of the points you find are not in the line as well. You can't take these points. That's why it's dangerous. Some people make this mistake. They take the points they found and quickly find the gradient. Don't do that. Because sometimes the point you find is not in the line. The point you find is not in the line means invade. Clear? Draw the best fit graph. See, number of points almost here. Almost close. Very close. Above, below. Uniformly distributes. Exactly where it cuts the grid line, find it. From here, x2, y2, x1, y1, y2 minus y1 divided by x2 minus x2. From there, you can find the gradient of the graph. From there, you can find the gradient of the graph. Okay, no? So I hope practical 5, practical 6 was good. Even the future practicals will do like this, so we can save time in the class and do more work there. And these much more easy for you all as well, because you can see the video as well behind it. And then you can, be attentive and leisurely do this. Okay, no? So enough for today. I'll catch you all next time. Take care. Good night.